You guys could turn your cameras on and we can meditate together. Everybody. Let's meditate for just another minute or so. And really give it your all. Just be very still. You can feel your third eye. It's a good place to focus your attention. Welcome, everybody. So today we're doing, how do I sound, by the way? Does that sound good? Does it sound better? Got a new mic. But I hear myself a little bit, which is a little weird. Mute the speakers. Okay, well, I muted the speakers, but when somebody talks, I'll unmute the speakers. So, namaste, everybody. computer programming, mathematical programming. There's different kinds of computer programming. There's programming apps. But what we're seeking to do is really take the TI-84 calculator to the next level, take Desmos to the next level. And when we do this, we're bringing structure to the mind. It's absolutely essential to do this. We live in a world of people who don't think logically. People don't put a lot of time into this. They put a lot of time into other things. You can say there's the base instinct, there's the logical mind, and then there's intuitive heart intelligence. And you go higher and higher. It's good to have this very strong intellectual mind layer. And when we sit down and challenge ourselves to produce, in the case of today, Turing pattern programmatically, it's a very, it's going to inform your subjective state and help you be more capable of being a refined, powerful being who directs your attention and thoughts in a powerful way. And that's essential for doing one of the most difficult things in the universe, if not the most difficult, which is becoming enlightened or progressing along the path to enlightenment. So it's a very difficult thing. That's why, there's not that many Buddhas, Siddharthas, Muhammads around, right? There's not that many of them. Even in the modern contemporary versions of those people, the Krishnamurtis, the Oshos, and the Anandamayamas, they're not that many. So today we get to refine the mind, make your mind very clear, and you'll notice perhaps that your third eye starts to feel very powerful and active. One day you'll be sitting talking to somebody and you'll be like, wow, I feel good. And this happens from doing this. I've been coding a whole bunch today, and I love how it makes me feel. Right. So think about it that way. Right. This is not the same as in school where it's you generally are left feeling not so good when you put yourself under strain. So we want to strain ourselves, but I wouldn't call it strain. We want to give ourselves the opportunity to refine the mind. It's not a strain at all, actually. We want to do it without conflict. And so let's dive in. So actually, Turing patterns, I sat down about an hour ago and I was like, whoa, I haven't thought about them in a few months. And I thought, okay, I'm a little rusty. So we'll go through this process together. I have a rough draft of it, but we should go through this. I did get a little help from ChatGPT. I was just quickly reviewing just a quick Turing pattern and trying to understand how it works. And so when we go through it, ChatGPT offers a really wonderful way to be more efficient. Before ChatGPT, we had to go and look on the internet, try to look at documentation. It was basically the same thing. ChatGPT just brings it all together very quickly for us. But once you look at ChatGPT, it's good to really rewrite it, because ChatGPT does not do it always the best way or your way, right? And so think of it more as documentation. It's not enough to just copy and paste it. Of course, it not only does it not really work, a lot of times it just doesn't work. And if it does work, it perhaps doesn't work in the way that makes sense to you and feels good to you. So let's take a look. Anybody know where Jacob is? Oh, yeah, I guess I have my speakers off, so if anybody said anything I didn't hear, give me a second. Okay.
Testing. Can you hear
So,
us?
this is actually kind of a difficult topic. share my screen now. It's kind of a difficult topic. I hope it doesn't overwhelm anybody, but we can break it down. So here's the code that makes a Turing pattern that's not of the highest quality. So we're going to revise and refine this and go through a lot of these things. Did you guys look at the coding train by any chance? Did you go through I hope you guys went through the intro coding train video, because this is a lot, but we'll go through it. Oh, you know what? Maybe if I turn the speakers down. Okay. Oh, that's better. Okay, I'll be able to hear you and then not hear myself too much. Okay, so how does this work? I'm going to create a new tab. So what is a Turing pattern? How does it essentially work? So if we think of a grid of 9 squares, and let's say each of these has a value. So let's say this is 3, 4, 5, 3, 2, 1, 0, 5, 4. We want to compute something that's actually quite simple to compute. We want to say, what is the influence of the things surrounding the 3? So the 3 is surrounded by all of these values. We can consider all of the values or just the ones adjacent to it, so leaving out the corners. Let's start with that. So if we looked at all of these values, we might say, well, think of it as like, are these values going to pull me up or pull me down? So for example, the 4 pulls you up by 1 because it's 1 more than 3. The negative, the 1 pulls you up, so that's the 4, produces a 1. The 1 produces a -2. The 5 produces a +2, and the 3 produces a 0. Pretty straightforward, right? So I took the differences. Now, if I added all these differences, I would get 1. That's the Laplacian. The Laplacian, which is this confusing thing, it's kind of like a two-dimensional derivative, is basically saying, how much am I influenced by my neighbors? What is the dx, the derivative, the change between me and my adjacent neighbor? Now think of this as a super high resolution thing. We want to take this down to the highest possible resolution. So these are individual pixels. So this is the Laplacian. 1 would be the value of the Laplacian. Now we could have also added 5, which would give us a 2. This would give us a -3 from the 0. The 4 would give us a 1, and the 2 would give us a -1. And we would get a 1 less, I believe. So you could do it either way, but let's just ignore the corners. Perhaps you can think of it as the corners are slightly further away, but in a way they also influence it. So I'm accustomed to not using the corners. So this is the Laplacian. So let's take a look and see how would we write a Laplacian function. So the Laplacian is going to take, gosh, I almost want to just delete everything. Okay, I'm deleting everything. Okay. I don't like going through other code. I like the process. Okay, so first of all, let's create a float t value, t = 0. This is a global variable. And let's create a dt. That means every frame we're going to change by this number. This number is 1/60th. So if I were to say void setup, Let's do a size 500 by 500. Let's void draw. Yeah, this will be better. And let's just print, let's just say, okay, t becomes, we're going to print t, and we're going to say t becomes. This is, remember last week we were a little confused about when I said equals. This is saying t becomes, t is assigned to t and dt. So what this effectively does is it makes t bigger by dt. Oh, you guys will sleep better at night already. I mean, how can you live without the structure of t equals t plus dt, right? The reiterative structure. It makes the world universe make sense. Now there's another way to write this you might prefer, which is t plus equals dt. That's a shorthand version. It means t becomes t and dt. Plus equals means add. Any questions? Does that make sense? So it's saying exactly the same thing. T plus equals dt means t equals t plus dt. T becomes t plus dt. So I'm using this just so it's more explicit, because perhaps this is new for somebody, probably for a few of you. So it's more explicit, meaning this is a little bit of a shorthand, but we use that all the time. Another thing you can say, oh, by the way, did you see these 2 forward slashes made all of this gray? So it's a comment. So it basically is not being computed by the system when I put those. We can also say things like t plus plus, and t plus plus means make t plus plus is an even more shorthand for t plus equals 1. So t plus equals 1 is t plus plus. So t becomes t plus 1, that's t plus plus. And you may have heard of the popular programming language C++. That means C for like count plus plus will bring you to the next value. It just literally increments the values. So when we do this, okay, so if I want to be a slightly better teacher here, I will break this down a little bit more. So if I were to say just with a 1, so t equals 0, we're going to print t, and then we're going to write t equals t plus 1, and it's going to increment it. So if we look down at the bottom, you see it's literally counting about 60 per second. We're tapping into the power of our compute here, right, of the computer. So what's happening? Every time it runs through draw, it increases t by 1. And then it writes the value. And initially at the top, we said t equals 0. If I said t equals 0 here, it would just keep bringing it back to 0. Right? So if I put it here, they're all going to be zeros. Because it's going to go plus 1, and then it's going to go back to 0. So this is a recursive function. Recursive meaning it's defined based on what it was. Any questions? Really encourage questions. I'm going to try and break it down step by step. But if you have any questions not completely clear, then you should say something. T++ will do the trick as well.
Yeah, I'm clear up to this point.
You getting it?
I'm clear up to this point. No problem.
Wonderful, wonderful. Better if you're getting it, you don't have to say anything. If you're not getting it, say something, because I want people to feel comfortable saying don't get it. And if you don't get it, you actually are contributing to other people getting it in a more rich way. Because Ayush doesn't get it, but perhaps he doesn't get it through the eyes of somebody who's getting it for the first time, or is not getting something, right? It really helps us to teach, and that's being a mentor is a wonderful thing. We learn so much from a 6-year-old, between the 6-year-old, learn so much. Not only about seeing math again for the first time, but their purity. We learn a lot from their purity as well. So now if I were to say t plus t equals t plus point 0.01667. Now, why am I doing this fraction here? That's 1/60th, and the system is set to 60 times per second. So then I'm actually getting the time. Every second will go up by 1. So now it actually goes up by 1 each time. So 1 second, 2 seconds.
Adam, your mic is a little blurry now. I'm not
Blurry.
sure what changed.
Huh. Can you hear me now?
Yeah, now it sounds really good.
Okay. It must have just been the system. Okay. So now, why did I put this number here? Well, I could also just say dt and define it at the top. So dt equals this. And then I could say t plus equals dt. And we have kind of what I was showing in the first place. So this is how I keep tabs on the time. Now, why is this perfect? Because we're gonna, if you want to create a video, and everything is based on t, this is the actual t. There's other ways to measure the time. We can say how many milliseconds has occurred, but that is very unreliable. Sometimes it takes more milliseconds for one frame to happen than for another frame to happen because the computer is maybe not running at full speed. Right, so this is actually kind of the thing that I developed to maintain time. And it's I mean, a little vulnerable sharing my personal sites because like if you ask ChatGPT list the frame and say frame plus plus, to me it's not as nice. I want a t variable as a math person, and I want my t variable. So any questions? All right. Now, perhaps we won't be able to finish Turing patterns today. I mean, it's maybe potentially like a 2-week course to be able to do the Turing patterns, but we'll do our best. Okay, so the next thing is, now I'm going to say t equals t plus, just to be explicit. And we don't need to print t anymore, but now we're using this. So I'm going to just kind of leave that at the bottom, out of the way. Okay, so I can make a background. Let's make a background equal to, well, what I can put something in here to determine the background color. If I put 0, it makes it black. If I put 255, it makes it white. If I put anything in between, it makes it between black and white. So this is a grayscale way of altering the background. Now I could say something like, let's just put t in here, and let's say t times 10, and you'll see every second that value is going to go up by 10. And we'll watch it go from black to white. Cool. Well, it's not quite at white yet. Let's print line here, t, so that we can print line. So we can actually see how much time has passed down here. Okay, so for Turing patterns, it's nice to make a white background. I'll just leave it white. All right, now what? Well, let's create that. I mean, okay, so let me explain something. So in the grid, Turing patterns are a reaction diffusion equation. That means we have 2 substances, a substance we can call U and a substance we can call V. One of them, they interact with each other and will eliminate each other and produce each other based on their concentrations. So just think of it as we've got 2 kinds of ink here. And the ink is not just more ink, it's actually going to, if certain concentrations are there, it'll eliminate itself. and then sometimes it will create itself. So it's having a reaction. You know what we should maybe do? Let's just do diffusion today. I'm going to start with diffusion. I really want to help you guys get this. I feel confident, and it's fun to go through and just really do it from scratch. So what would be diffusion, for example? So let's make an array. Oh, even arrays are a little much. Do you guys know what an array is? Probably not. An array. Okay, two-dimensional array. That's a lot. Let's see. Okay, the universe said do it. Okay, so an array. An array is, so a float array like this. We can name this. This is like float, and then these brackets means make a list of decimal numbers. Okay, what should we call that list? List. We'll call it list, okay? We can call it anything we want. I could call it Robert. List of decimal numbers, and we want to define this list as a new, make sure I got my syntax right. Okay. So you'll say like new float, and then how many numbers are in this list. So this is a very confusing line, but let me just explain it because it's really not that confusing when somebody explains it. This is the type of thing. This is the name of the thing. And then we want to say, so it's the type of thing that goes by this name. And then we have to say new. We're going to say it's a new, and then it's a, we're like assigning that it's what kind of version of that type. It's a type that has an attribute of 100 in it. So the type is a float, means decimal point, brackets means list, a decimal point list named list, and we're going to set it with the attribute that it has 100 parts in the list. Okay, so if I were to do this in setup, I can. Well, so here's another thing. This is you guys are gonna have to review some of this. So I can say for I equals 0, I is less than 100, and then I becomes I plus 1. So in this, if I were to print line I, what, and we're going to just no loop this. So the draw won't loop now. We're just going to basically focus up here. What I've done here is I'm doing a for statement. A for statement, which is completely independent of this, is saying for I values starting at 0, but only while equals less than 100, we're going to do this. And we're going to do it every time we go cycle through this, we're going to increase it by 1. So if you do this, we'll see it just counts straight up to 100. See it count from 0 to 100. I could say, okay, what about I times 3? So I goes from 0 to 100, but now it's going to print I times 3. So it goes from 0 to 300 by 3s. Another thing you could do is say I plus equals 2 right there. So I increments by 2 each time. So now it went up by 2s, and we're just printing I. We could make I increment by 0.1111. Now this is going to have way more values, right? Because it's going to go all the way up to 100, but we're having many, many, many values between. We can say start at 90 and go up by 2. So you see, it only went from 90, 92, 94, 96, 98, because it's saying start at 90, go up to until it equals 100. And now notice it didn't say 100. If I say I is less than or equal to 100, now it will actually say 100 because it needs to satisfy this condition in the middle here. So this is like a while statement. There's another way to write this that kind of is a little bit more manual, where we say do this while these conditions are true, starting at this, and do this each time you loop through it. So let's see. How would I perhaps count down from 50 to 30? So I can say I equals 50, while I is greater than equal to 30, and I equals I minus 1. So this will count down from 50 all the way down to 30. Am I giving you guys, if I say my I minus 5, it'll count down to 50 to 30 by 5s. Okay, so Robert, you're getting it now? That makes sense? What this is? Cool. So now, why did I go through this whole entire thing here? Well, the reason is I would like to start I at 0, and I'd like to do this until until I is 100, because there's 100 things in this list. And if I plus plus again, fine. So I plus equals. Okay, so now when I do this, I'd like to set, instead of just printing the values, I want to go to the location in that list. And I want to set that equal to a random number between 0 and 1. So when we can access locations in this list using this bracket syntax, list, brackets, and then what location, where 0 is the first location and 99 will be the last location. There actually is no location equal to 100. It just means there's 100 of the locations starting at 0, ending at 99. Now, we have to put a whole number in here, an integer. We can't actually use a float anymore. So I have to say int. So notice how it gave me that little error right there. Right here it says float does not match with int. What it means is we need to use an int we want our I to be an int. So it's going to literally cycle through I is 1, I is 0, 1, 2, 3, 4. And for each of the locations, it's going to assign a random number. Isn't that great? So this all happens in setup, which only happens once. So if I go down here, I can say, okay, I'm realizing that Turing patterns are kind of not possible for today. Okay. So, because there's a lot of, you have to understand all these things to do Turing patterns, basically. And this is a lot. It's a lot. If you guys feel that I'm talking fast and this is a lot, that probably would make sense. I'd rather go a little fast and then have you slow me down instead of go too slow, which can make everybody feel more comfortable. But you know you're in a loving place, right? We accept whatever. If you're like, Adam, why I? You can say anything. We want you to, like, oh, by the way, it doesn't have to be I. I can call this Robert. Robert is 0. While Robert is less than 100, Robert becomes Robert plus 1. And then we're going to use Robert in the list. Then that will work just as well. Now, we like I. I is a very common number to use it, but sometimes you use X, sometimes you use Y, sometimes you use J. Usually we think I, J, and then K. Those are kind of the, sometimes if we're using I and then we put the I inside of a J, we need another one, so we have to use a J. So, okay, we won't use Robert. So if I were to now go down here and basically do it again, but this time I'm going to print the numbers in this list. So print list I. Print line list I. So this will actually print those random values. It's 100 random values between 0 and 1 are now being printed. I could print maybe just the first 10 values if I wanted to. So these values are static now. They're all there in this list. We put them into the list up here, right? So I could say, let's make that 10. So now we're going to populate the list with random numbers between 0 and 10, and then we're going to show the list. So that's what we're just doing here. We're just showing the list. Okay. Showing the list. So this is useful in Turing patterns because we want to create a, let's try this actually. Let's pretend these are X values. So we're going to just go X values. And instead of going to 100, let's go to the width of the screen. So this turned blue because it recognizes that the width is already 500. That's actually the first number. So now we're going to populate X with, we're just calling it X now, but there's actually going to be 500 values. And we could do, we could give it the number X actually. So if we did this, okay, so you see how it says out of bounds? That's because this needs to also be 500. Basically, we didn't put enough spots in the list, and it said, wait, there's no more space here. You wanted me to go to 500, but you only made me 100 long. So 100 spaces, not 100 spaces in it. So now, now we've got all these values. So what would happen if I go let's okay, so in this list of X values, we can now draw a point. Let's draw a point, and we're going to make the point have a color equal to the value. Remember how I made it go black to gray? So we're going to have the point have a color equal to the value of the list. So remember, these go from 0 to 500. So we're going to get to white pretty quickly, which anything above 255 is white. And we want to, so stroke tells us the color of the paintbrush, so to speak. Stroke weight tells us how big we want that dot to be. So we want this to be 1 pixel. And then we're going to draw a point at X, at just X actually, comma 0. Or let's do X comma height divided by 2. So it's in the middle. So if I do this, we should have a line getting wider. You see that? See how I did that? It's a line that starts black because X value is 0 in the beginning. And by the time the X value gets to 255, which is half of 500, there we have it becoming white. So let's just make sure everybody gets this. You guys get that? So what did we do? We said make it the color of the X value. I mean, in a way, I could have just put X here, by the way, right? Because we already said X, the value in the list is X. But the point is, we want to, well, here, maybe we could do something a little bit more interesting. Like, let's say we want this to be the sine of X divided by width. So sine is a function. X divided by width will go between 0 and 1. Let's multiply this by tau. So now it goes between 0 and tau. So the values in the list, based on the X value, will go between 0 and tau. Well, the sine goes between 0 and tau. So this is going to oscillate between -1 and +1. Okay, so maybe that's too much. Let me just go back. So okay, so so this line is fading. I like that. How did we do it? But what if I said something like X divided by 2 now? So now when we do this, the line will go all the way across. Why did it do that, Ayush? So the biggest value was X equals width. So the biggest value in the list went to width over 2, which is 250. So we only got to the white at 250. Now, notice we're doing all of these for X equals 0, sorry, Y equals height over 2. If I wanted to, I could say for, basically, copy this. And now I'm doing a list, I'm doing a loop inside a loop. So for each, and I can say Y here, Y goes to height. And then instead of H over 2, I can just say Y. Now, what is this effectively doing? For each Y value, from Y is 0 to the full height, it's running this whole line that we just did. So it's an incredibly large number of data points. It's actually 500 times 500, which is what, 250,000. So there's a lot. It's amazing how fast a computer is. Now, when we do this, you'll see a beautiful gradient. Now, I did that. Why is it not more black in the beginning? I'm not sure. Let's find out. It should be completely black in the beginning. Well, X starts at 0. Oh, you know why? I think that why it's not. Let's make this 1 a 2. We're actually drawing dots. Sometimes the dot's different than the pixel. The pixel is a little harder to do. It should be blacker. Yeah, there you go. The reason was it was like the dots were slight, like little round dots, and then the corners of the square inside the circles inside of were not calculated quite right. So now if I make it X over 2, So there's a gradient. So what did I do here? I interfaced with I basically drew 250,000 dots. You saw how quickly it drew that. It's amazing. And calculated what their colors are going to be for all 250,000 dots. Perhaps we can do this in a slightly different way. Watch this. This might make a little more sense to people. Okay, this will be cool. Watch. See what I did there? So here I'm, what happened? Well, I'm actually jumping through the list very quickly. Every time I jump through that list, which is 500 long, but I'm jumping up by 20 spots and finding out what the value is. And then I'm drawing a big dot instead of a little dot, right? Because I could draw a little tiny dot in each of those spots. Right? You can see tiny dots. Those are 2 pixel dots. Or I could draw a 20 pixel dot, which will be touching its neighbors because we jumped by 20. So you see how I'm able to think like this? This is what it would be very advantageous for you to learn to think this way. Now you can start with just drawing these dots. I mean, I remember when I was first starting, I was like, oh man, look at those dots. I just loved how they were all perfectly spaced, and I was controlling the color, and I can make them any size, and it looks art. It already looks like artwork, right? So it's pretty, right? It's like, you know, you could put this on through. See, it's all fading out. So, okay. So to make Turing patterns, okay, so what is diffusion? Let's try and do diffusion first. So what if we were to say, to do diffusion, we have to do 2-dimensional arrays, which I feel is kind of silly for me to do right now. A 2-dimensional array is like a list of lists, but it kind of starts to act like a 2-dimensional coordinate system with a lot of cubby holes in 2-dimensional space instead of 1-dimensional space. And then we could, yeah, so I think this is maybe a nice intro. Really would help if you just watched the Coding Train 4-hour intro, because he'll go over all of these things. And I'd rather, you know, hit the ground running with you guys and dive into things like Turing patterns, just to take a look at now how complicated this looks. We've got 2-dimensional arrays. We actually created 4 of them. We've got these constants here. We're initializing those 2-dimensional arrays. We're populating those 2-dimensional arrays. We're populating for the U and the V values. We're updating the V values for part of one of the arrays in the center. Let's see, we've got a nested for loop here, a loop in a loop. We're actually using this to calculate, do the differential equation. Here's the Laplacian, which all the way at the bottom has to do with adding the things adjacent and next to and subtracting 4 of them, which is basically what we did in the very beginning. You have to load the pixels, present the values. You have to update each iteration. You have to update by storing it into a temporary buffer. And that's it. but that's a lot of stuff. Right? So that's, we're just making sure you understand arrays and for loops for now, and time. But all of that makes oh, so when you watch this, it grows. This is all happening because it's actually interfacing with the cells around it. So you got the 9 cells, and then each of them is affecting each other, and it's spreading, but it's also eliminating itself. And it has this deterministic ability to draw these patterns, which Alan Turing hypothesized were the reasons certain animals have stripes and dots and spots and things. It looks kind of like a fish, right? Those fish that have those lots of spots on them. So this is a Turing pattern, and it would be great. I really offer, you guys are welcome to give me feedback on how to do this. I think you guys are at relatively the same level. I'm not sure, perhaps I'm wrong about that, but there's advanced coding classes where you just, okay, we're gonna do Turing patterns from scratch right now in an hour. And that's what I wasn't sure if people would want that. There are some people that like, how do you do Turing pattern? Let's just see if we can do it. But they already know all of the other stuff pretty well. That's strange, it's growing this thing. Isn't that cool? And if you look at my animations that I've done on Instagram, you'll see some of them are actually 3-dimensional. I created meshes, and I changed the Z value of the mesh to be based on what the Turing value is. So it creates this almost like tactile labyrinth. I did one of them. I created one of them. I took the data from an image and changed the parameters for the reaction so that it actually drew a person, which was really, really cool. Did you see that one? Wasn't that cool? I don't know if people can appreciate the fact that it literally drew a person with Turing patterns. So that was fun. So many things you can do. So it's wonderful to do basic things as well. Can you just draw a bunch of circles in a grid? Can you randomize the colors of the circles? That's fun, right? Can I just draw a bunch of circles that are all different colors? It looks like candy, there's so many fun things you can do. So I'd like to recommend that you guys explore that this week. The more you explore, I was recommending 15 minutes a day. If you have time, you might even do an hour a day. This could be the beginning of your coding things. Now, if you just do 15 minutes a day, that's fine too. You might say, oh, I just want to make a list of the Fibonacci sequence. Or maybe even simpler than Fibonacci is just saying, 1, 2, 4, 8, 16, 32, 64, just doubling, or just counting up by 5s, 5, 10, 15, 20, right? These are all things you can do. Now, I would argue that if you can't do that, think of the opportunity to to refine your mind, to be able to think this logically. And it's not just about computer programming. We're learning to store information in a list, access it programmatically. This reflects in your life. You see that bookshelf behind Robert? How would that bookshelf change? It's a list, right? There's lists everywhere. When you make dinner, it's a list. This, then this, and this. based on order. It really helps you to empower your mind. Okay, so nice. Thank you, Corinne. So, Robert, I'd love to hear from you.
What would you like to hear? I do have a quick question too. I looked on the coding train. I couldn't find like a intro video, that was 4 hours long. I looked for it, but I couldn't find the actual one you're talking about.
Okay,
So do you know what we might type in to be able to find that exactly?
you go to his website?
I think so.
Or
I
did
think
you-
I ended on his YouTube and
if you go to the website,
okay.
It should be like right up there in the top, or if you just look at the list, it's like.
I'll share the link on the Discord.
Okay, great.
Okay.
Oh, good.
Thank you.
So, yeah, I think it's a good thing to do to accelerate our work together. It would be fun for us to do Fourier transforms and I don't know, platonic solids. There's so many things we could do together that it'd be more fun. Well, it wouldn't be more fun for me. I like sharing the basics too. So it's up to you guys. All right, let's do a little meditation.
We can also discuss the basics on the Discord. If you don't get something correctly, then you can question there.
Yeah.
If I could be any help, then I'll also help.
Wonderful. I love that. Yep. I love that. I love that you guys are doing the Discord. That's cool. I haven't shared it on my, oh, yeah. Somebody took my name. I tried to sign up for the Bhakti Math Guru in Discord and somebody already used it. It's really annoying. Like I know that was them, just they knew about me and they decided to take it for themselves. Oh man. All right. So let's do a little music here.
We'll keep it to an hour today. Can you guys hear? It's good to make sure you're centered in your heart. We do computer programming, bringing clarity to the third eye. And still centered in the heart. All right, everybody. Namaste. I will see you guys tomorrow.
And I just shared in the chat the code from today, so you can review it if you like.